Hey class, I am excited because we are talking about confidence intervals today. Confidence intervals and a hypothesis test is the main big rocks of this particular course. That's what we are shooting for, is figuring out those. That's what inferential statistics is all about. So let's talk about confidence intervals, which is under the topic of point and interval estimation. So the word estimation means really we're talking confidence intervals. Now, let's go back to what we were talking about last day. We said that this is the kind of problem that we have been dealing with in Unit N, where x is normally distributed with a mean equal to mu and a standard deviation equal to sigma. And then we said, well, what if we don't know that the population is normally distributed? Not a problem. As long as your sample size is at least 30, then the central limit theorem kicks in and it says regardless of the parent population, then the distribution of all possible sample means, that is the x bars, will be approximately normally distributed with a mean equal to mu and a standard deviation of sigma over the root of n. That's what the central limit theorem says. And then we said, well, what if we don't know what sigma is? Because really practically, we are taking a sample to infer the characteristics of the population. And we said, well, that's not a problem because instead of using a z distribution, we use a t distribution, which uses s, the sample standard deviation, instead of sigma. And now we're going to say, well, what if we don't know what mu is? And in fact, that's the whole point of confidence intervals, is to estimate what mu is. Or in hypothesis testing, is we will test a particular hypothesized value. So, as I mentioned before, this is exciting because it means that we don't need to know anything about the population, how it's distributed, what its mean or standard deviation is, but we can still come up with good scientific probabilities for certain events here. So let's talk about confidence intervals. And what we've got down here then is some statements, and I'll let you read through this on your own when you get a chance to. And it says that x bar is an estimator of mu, just like S is an estimator of sigma. In other words, your best guess as to what a population mean is a sample mean. Your best guess as to what a population standard deviation is the sample standard deviation. We call these things point estimates. So they're single numbers, which are our best guesses. The problem is that there's this thing called sampling error. Sampling error doesn't mean that you messed up somewhere in the process. When we get into 307, we'll talk about constructing good survey instruments or questionnaires and how to gather good data and so on. And there's this thing called non-sampling errors, which is where there's mistakes made in the process. But sampling error is a pretty natural thing. And it just simply says that, let's say the average height of college students, and we'll talk about just the males because of course there's a difference between males and females. Let's say the average height of college male students is, say, 5'10" and a half. I'll just throw a number out there. And I could randomly take a bunch of students, so they're not all athletes, they're not all engineers, they're not all artists, they're not all business students. They're from a variety of different programs, of different nationalities, of different ages, and so on like this. And I could take this sample, let's say it's 100 students, and I could line them up against the wall here and get out the measuring tape and figure it out. And what I would likely find is with 100 students, I would probably get pretty close to the college average of 5'10" and a half. If this is a good representative sample, right? If I only sampled, say, the phys ed students, then I might get actually a taller sample average because it's not representative of all of the college students. But if I have a good cross-section, random sample, of college males, and then I determine the average height of that sample, it would probably be pretty close to 5'10½", but it might be a little off. It could be a long ways off, actually. I could just, out of sheer dumb luck, end up with a lot of really tall guys or a lot of really short guys. But I'm likely to get some really tall and some really short and some average kind of height guys, and it would probably average out pretty close to 5'10½". But it probably wouldn't be exactly that. And so there would be some what we call sampling error. So what we do in confidence intervals is we come up with an X bar from a sample, and then we build a buffer around it. So here's an X bar value that we get, and then what we do is we build a buffer around that, and we say, well, we're, say, 95% certain that the true mean, the mu of the average height of all the college males, is somewhere in this range, somewhere between here and here. So this thing here is called the margin of error. And we'll see that a little bit later. All right, let's talk about how we get to that point there and how we do the calculations. So I'm going to start with something that you're going to say, I don't know why we're doing this, but I'll show you where it fits in quite well here. Find two values, let's call them Z1 and Z2, such that 95% of the Z distribution lies between these two values. So let's put Z1 here, and we'll put Z2 here, so that 95% of the distribution lies between them. This is a symmetric thing, and so it's the middle 95%. Now, here's the thing to note here is, remember that this is, when we're talking a Z distribution is centered on 0, has a standard deviation of 1, right? So it's normal with a mean of 0 and a standard deviation of 1. And so it's symmetric, and what we have here then is that, well, 47.5% would fall in this area here, right? And then we would have another 47.5% in here. And then, of course, we would end up with 2.5% in here, 0.025, and 2.5% here. That's what the thing would look like. And we want to find, well, what are the Z values that have those proportions here? Let's go to a Z table. And remember, the Z table gives us this area here. So let's go back to, what page is that? I think it's 160. There. Right, so here's the picture up here, where it says we've got 47.5% here, and we've got 5% here. 2.5% there. This would be the Z2 value. What is that? So we look up 47.5% in the body of the table, and we get 47.5% is right there. This is one of those magic stats numbers which you will remember. It's 1.96 right there. Okay? So let's go back to where we were. By the way, I just want to stop off at the t-distribution here. And in the t-distribution, remember I said that the last line of the t-distribution are just Z values. So let's take a look at that. Last line of the t-distribution are Z values, and here's your 1.96 underneath the 2.5% column. Remember, a t-table is giving you this area here, 2.5%. That would leave you with 47.5% here. So you end up with the same as the last line of the t-table gives you Z values. And these are common values that we'll use in confidence intervals. 2.5%, 1%, 0.5%, 5%, 10% in the tails. You'll see how that works in a moment here. So getting back to confidence intervals here then, we said that these values here then are, this was plus 1.96, and this would be minus 1.96 because it is a symmetric distribution. So those are the two Z values that we've got, plus and minus 1.96. Let's write that as a probability statement. So we are 95% sure, or 95% of the Z distribution lies between minus 1.96 and plus 1.96. But Z is equal to this. That's what we learned at the beginning of this unit. So let's replace this in the middle. So that's what we've done down here. And now what we're going to do is we're going to solve for mu. So I've just done a little algebra here, taking stuff over to the left and right, and that leaves us with this. And this is called a 95% confidence interval for mu. What we mean by that is that we are 95% certain that this interval will contain the population parameter mu. So you can see we've got a mu is somewhere between, and what we do is we take our x bar value, our sample mean is our point estimate. It's our best guess as to what mu is. But then we build, a buffer around it. And this buffer, so plus or minus 1.96 times sigma over the root of n, is called the margin of error. I'll write that out in a moment here. So it's not likely to be exactly x bar. We take the x bar and build a buffer, plus or minus an amount here. So that's how we do this. Let me show you how that works actually. And so it says right here, thus we say that we are only 95% confidence that the interval contains the true mean. Or we can say that this procedure of taking a sample and constructing a confidence interval contains the true mean 19 times in 20. 19 divided by 20 is equal to 95%. Now, one thing I want you to note here is that, well, why couldn't we be 100% certain? The only way that we can be 100% certain is to take a census. Sample everybody. And so if we're trying to infer the characteristics of Albertans, or let's say even bigger, Canadians, then we would have to sample everybody in Canada, and we just don't have that kind of money. Even Stats Canada, I mean, that costs them a lot of money to do a census every 10 years, and even then, they don't get everybody. There's still some people who are hiding out in the bush, or they're transient, or where they don't have homes, or things like that, okay? So what we have to be okay with is a certain amount of uncertainty when we're dealing with taking a sample and inferring from it the characteristics of the larger population. Now, the level of confidence is something that we'll talk about a little bit later, but it depends on how certain you need to be. And so, for instance, if I'm looking at, say, putting a new cancer drug out on the market, I want to be, more than 99% certain of my results, that it's safe, that it's effective, that kind of thing. And so I'm not going to put that out unless I'm at least 99% certain that this is not going to cause me any problems and that the thing actually works. With business decisions, we typically say that we need to be 95% certain. So that's the usual level of confidence that we tend to have for most business kind of problems. But that can vary, and we will talk Not so much in this course. I think we'll start actually in Business 307 by talking about what we call Type 1 and Type 2 errors. If this is your last stats course, maybe just pick up your stats book and you can take a look at Type 1 and Type 2 errors. Let me put it to you another way, though, and that is to say, suppose I want to be a I want to make sure that my confidence interval that I build contains the true mean. Let's say I'm estimating IQs of college students. Well, I could say something really absurd in terms of that the average college IQ is somewhere between 10 and 250. Now, that's absurd. It's true. I mean, I almost certainly, well, for certain, really, in terms of what we know about IQs, is that that interval actually contains the mean, somewhere between 10 and 250, but we really haven't learned anything useful there. When we can say that, well, we don't want to be 99.9% sure. We're okay with being just 95% confident. And what that does is it actually shrinks the confidence interval quite a bit. So we can say we're actually confident, we're 95% confident that the average college IQ is between 105 and 120 or something like that. So that's much narrower. And if we want to be even less certain, we can say we're 90% certain that it's somewhere between, say, 110 and 115. So, by the way, I don't know what the average college IQ is, but I'm just using that to show that the level of confidence that we have actually determines the width of the confidence interval, or what we'll call as your margin of error. We'll see how that works with the numbers. Let's get back to a 95% level of confidence, which is typical with business problems. Again, we can't be 100% confident unless we sample everybody. So we're typically okay with a 95% level of confidence. So what I've got here is an example. And so this example here is, we've got I think this is our problem that we've been dealing with before, where the mean is equal to 60 and the standard deviation is 12, like the marks of 50 students, which we looked at all through Unit N and even back in Unit C and so on like that. So we've been living with this particular problem a lot. X is normally distributed with a mean of 60 and a standard deviation of 12. And we're going to take samples of size n is equal to 25. Now, I'm just going to take 20 samples here. Theoretically, we could take as many samples as we can and take all possible combinations. Practically, we only take one. But I want to show you what happens if we take 20 samples. So I'm using just a little program here called Minitab. I think I mentioned to you before, it's a stats program. It doesn't really matter that you know how it works, just how to read these things here. And so this is your X bar column. And so these are sample means. This is your S, standard deviation. And this thing here is actually sigma over the root of n. So in our case would be 12 divided by the square root of 25, which is 2.4. This is called the standard error of the mean. And so sigma over the root of n is the standard error of the mean. Standard error of the mean. When you look in your descriptive stats output in Excel, when you're describing a column, you'll actually see something in there called the standard error. Now, it's calculated as S over the square root of n, so it's taken from the sample. It assumes that the data is a sample, and so it's S over the square root of n. But if we know what sigma is, then it would be sigma over the root of n. Now, what we do here then is we're using this formula up here, right here, And so it would be x bar plus or minus 1.96 times sigma over the root of n. So let's take a look at this first example here. So this is 57.18 plus and minus 1.96 times sigma over the root of n, which is 12 over the square root of 25. That's that 2.4. And what that gives you here then is these guys, which are the lower bounds and the upper bounds. 52.47 and 61.88. So the way that we would write this is like this. And the way that we read this is that we are 95% certain that the average, in this case, marks of students, are between 52.47 and 61.88. So that's the confidence interval. So that's where we get these numbers from. Now, here's the important thing then, is that that's one sample. What if we did that, say, 20 times? And so in the next one here, we end up with 60.81 is the x bar. The next one is 59.02 and so on. And in each case, we build a confidence interval. Now, when you take a look at these 20 confidence intervals, our hope is that they contain the true mean, which is 60. Remember, in practical problems, we don't know what the true mean is. That's why we're taking a sample, is to infer the characteristics of the population. But take a look at this, and what you will see is that in almost all of them, the interval contains 60. So it's got a lower bound in the 50s and a higher bound in the 60s. There is one, though, which is right here. And that's because just by sheer dumb luck, we ended up in our random sample of a very low sample mean, about 52, 51.98. And so when we built the confidence interval around it, it actually was a little short. It didn't hit the mean. And so what we found here is that 19 out of 20, which is 95% of these confidence intervals, contain the true mean. That's what this is all about here. Let me show you another way of looking at it. So here's the distribution of sample means, the x bars, according to the central limit theorem. Or in this case, if the original population was normally distributed, then this would be the first limit theorem, right? First limit theorem says that if the original population is normally distributed with a mean and a standard deviation, then the distribution of the x bars will also be normal with a mean of 60, the same, and a standard deviation of 12 over the square root of n, which our case is 25, right? Central limit theorem says, well, as long as your n is large enough, this 25 isn't large enough, but the original population is normal. So the first limit theorem kicks in. But if n was at least 30, it doesn't really matter what the original population is. You'd still get this nice distribution of sample means. So this is the distribution here of the x bars, all possible x bars. And it's centered on 0, and it has a standard deviation of sigma over the root of n, which is 2.4 in our case, 12 divided by the square root of 25. Now we take some samples. So here's one x bar value, and we build a confidence interval around it. So this part here is called the margin of error. Margin of error. And so that's this part here. That and that. So we're saying that we're 95% certain that this interval contains the true mean. Now in this particular case it does. There's the mean of 60. So then if we were to do this again and again and again, so here's an example of 20 different samples. Here's another one. So this was a little lower, X bar value, but when we build in the margin of error, you can see that it contains the mean of 60. And again and again. But this guy is low. And so if you take a look at these, you'll see that there's 20 of them here. And you'll find that 19 out of 20 of them, or 95% of them, contain the true mean. But 5% of them, which is 1 out of 20, it doesn't work. Now, just to let you know, I've done this experiment using Excel a lot. So, for instance, it's really easy in Excel to do this, not 20 times, but 10,000 times. And what I found was that you can do this over and over and over and over again. And it turns out that with a 95% level of confidence, it's just about always, it's around 5% of them are outside of that limit, that they're either really small or they're very large, so that their margin of error does not contain the true mean. And 95% of them do. The size of the margin of error, though, depends on this guy right here, the 1.96, which is specific to a 95% confidence interval. So, returning to the algebraic derivation above, please note that the 1.96 on the Z table is the Z table value for a 95% level of confidence. If we want to be 99% sure, then we would actually have a larger number there than 1.96, and that would make the margin of error larger, so the interval would be larger, so that we're more certain that our interval contains the true mean. Let's draw a picture here and talk about how to generalize this. So back up here, what we did was we said, okay, this is very specific then for a 95% level of confidence. That's the 1.96, plus or minus 1.96. What we're going to do is we're going to introduce a symbol called alpha. And alpha is called the level of significance. This is really important in confidence intervals and also in hypothesis testing. It's the amount of allowable error, in a sense. So what we're saying, remember, is that we can't be 100% certain of our results unless we take a census, which is usually too costly. We don't have access to the whole population, all that kind of stuff. And so we have to be okay with being less than 100% certain. Alpha is the amount of what we call the level of significance, the amount of allowable error that we're okay with. So we want to be 95% certain. That means that there's a 5% chance that our confidence interval will not contain the true mean. So that gives us, if alpha is the level of significance, 1 minus alpha is the level of confidence. Now this is how it works, is you've got 1 minus alpha percent here, and that leaves you with alpha over 2 here and alpha over 2 here. So when we're talking about 95%, then alpha would be 5%, and that leaves you with 2.5% in the tail. That, of course, is what we had up here, right? Is we had 2.5% in each tail. Oops, let's see. For a 95, let me change colors here. For a 99% level of confidence, then alpha would be 1%. That's what's left over, and that means that alpha over 2 is 0.005, and so on. 90%, alpha of 10%, alpha over 2 is 0.05, and for 98%, and so on like that. So you could do that for any level of confidence. These first three in particular are really three common levels of confidence. So we're usually talking about a 90, 95, or 99% level of confidence. So the general form that we have for a confidence interval looks like this. So instead of having 1.96 here, we have a z value, which is based on alpha over 2 in the tail. That's what that means. And 1.96, of course, had 2.5% in the tail. So that's what it looks like here. Now, what I want you to notice here is that the left side is exactly the same as the right side, except that this is x bar minus, and this is x bar plus. And this part here is called the margin of error. Let me write it down here, actually. So this part here is called the margin of error. This is the point estimate, right? X bar is our best guess of what mu is. This guy is called the standard error. Standard error of the estimate, of our case, it's of the mean, because we are estimating means, mu's. And then this is based on the level of confidence. Okay, so I just want to go back up here and show you for these levels of confidence here, 95, 99, and 90%. Let's go to a Z table. And actually, we don't even have to go to a Z table. As I said, we can go to a T table, because the last line of a T table has common Z values associated with common alpha over 2's. So here's the 2.5% column, and here's 1.96. When you're talking about a 99%, a 90% level of confidence, then alpha over 2 would be 5% in each tail, and that would be 1.645. If we're talking about a 99% level of confidence, then you would have 0.5% in each tail, and that Z value would be 2.576. And we could look those up on a Z table, and you'd find the same numbers there, right? A bigger number here, 2.576, is bigger than the 1.96, so that will give you a bigger margin of error when you stick that into the formula here. Right here, bigger margin of error. Now, the thing to note down here then is that you can use a Z based on alpha over 2. That's just a subscript, the alpha over 2. It doesn't mean Z times alpha over 2. Or you can use a T, right? If sigma is not known, then it would be a T alpha over 2, and then comma n minus 1 is just your degrees of freedom. Again, it's not t times n minus 1, which is a mistake that sometimes people make. That is what we've got there. Okay, and your standard error can be sigma over the root of n, or s over the root of n, or we could tack on an FPC factor, which is what we learned about before. Now, if you put that all together, you might remember that way back, what page was it on? I had that down. Let me see if I can find that. Was it about here? It was at the beginning of this unit here. Yeah, sorry about that. You might have remembered me saying that the reason why we write down these symbols of mu and sigma, and I'm really fussy about the formulas that will eventually end up with something that looks like this. And now we're there. And if you take a look at this, it looked really ugly before, but this is an x bar minus a t value times s over the square root of n times an FPC factor. And then is less than mu is less than x plus. And so we've now been introduced to all that stuff. This would be for a 1 minus alpha percent level of confidence. So let's go back to where we were. Right there. So it really comes down to this formula right here, where you can replace the z with a t and the sigma with an s, and you could be tacking on an FPC factor. All right, let's take a look at the calculations for that. And actually, we're going to leave that for the next unit here, where we're going to look for steps for calculating confidence intervals. But we've been introduced to the general formula, and so there's no homework for this particular one, but there will be some problems that we work through in the next one. So I'm going to stop it at this point.